Natalie.
And I'm Izzy.
And we're going to teach you about water potential today.
What is water potential?
Well, water potential is the potential energy of water per unit volume relative to pure water in reference conditions.
So what this really means is that water potential helps us figure out if water is going to flow into or out of a cell.
Ha ha! Wait, click on the thing. Oh, there's a penguin on my head. So, here are some things you need to know about before we look at examples of water potential. First, the equation of water potential is as follows. Solute potential plus pressure potential equals water potential.
And written out, the equation looks like this.
The symbol for water potential is the Greek letter psi. It looks like a trident.
Water potential is built on two things. It's built on the solute potential, which is water moving through osmosis, and the pressure potential, the physical easing of the cell.
What does this really mean? I don't know.
Well, solute potential is water moving through osmosis, meaning that water moves across a semi-permeable membrane from an area of high concentration to an area of low concentration.
Oh, so solute potential decreases when the solute concentration increases. So if solute is added to a cell, let's say, it will have a lower solute potential than before. And if solute is removed from a cell, if it were to diffuse out, it will have a higher solute potential.
Right. So how do we find the solute potential?
Well, solute potential is found with the equation negative I CRT. The I stands for the ionization constant in the equation. This number will be somewhere in between 1 and 2.
The C in the equation stands for the concentration of solutes. For this part of the equation, we are finding the molarity of the solution. This means that to find the value of C, you must divide the moles of the solute there are by the amount of liters there are.
The R in the equation stands for the pressure constant. Since this number is a constant, remember that no matter what equation you are doing, this number is always the same. This number is 0.0831 liter times bar divided by mole times degree Kelvin.
The T in the equation stands for temperature. However, the temperature that we need to find is in kelvins, not Celsius. So in order to find the T value, you have to add 273 degrees to the original temperature.
Always remember that there is a negative sign in front of the equation, so solute potential is always negative.
And what about pressure potential?
Well, pressure potential becomes relevant when we speak about water potential in plant cells. In a plant cell, as water comes into the cell, pressure builds up on the cell wall. But don't worry about that too much, we'll go into detail about it later.
And before we begin, remember this key idea. Water moves from high water potential to low water potential.
A fundamental component of understanding water potential is the difference between plant and animal cells.
In terms of solute potential, both plant and animal cells can permit diffusion of particles between membranes. However, in terms of pressure potential, plants and animal cells are very different.
So let's look at an animal cell. In animal cells, when water moves out of a cell, the cell will shrivel up. However, when water enters the cell will begin to swell. As water continues to enter the cell will get larger and larger until eventually the cell will die and it will burst.
Yeah. This is different to plant cells because in plant cells there is the presence of the cell wall. When water moves out of the cell wall, the plant cell will shrivel up inside of the cell wall, making the plant droopy. However, when water enters the cell again will start to swell. But this time, as water continues to enter the cell will start to put pressure on the cell wall, which creates something called turgor pressure. This turgor pressure allows the stem to stand upright, which is why many people water their plants so often.
So, let's say we have a cell, and we put it into a container of water that has an extremely high concentration of solute. The solute outside the cell, therefore, has a low solute potential. Because as we mentioned before, the higher the solute concentration, the lower the solute potential. Remember that solute potential is always less than 0. So in this case, let's say the solute potential is negative 6 bars. We use bars as units.
And let's say that the pressure potential of the plant cell is 2 bars, because it is, at the start, very turgid. The pressure potential will then be, let's say, around 3 bars.
So, according to our equation, the water potential will be what? Solute potential plus pressure potential. So what is that? Negative 6 bars plus 3 bars equals what? Negative 3 bars water potential. So this number can then be compared to the water potential within the cell to understand which way water will move. If the water potential is -1 bars, for example, within the cell, which is a higher water potential than outside the cell, the water will move out of the cell into the solution on the exterior.
Do you ever wonder how water moves up a tree?
I do.
Let's say we have a nice baobab tree from Madagascar.
Yes, that works.
So let's say we place distilled water at the roots of the tree. The water potential is, of course, 0, because water potential is measured based on pure water, which is 0.
Okay.
The roots have -2 bars water potential because they have a lot of solutes inside of them.
So what will happen?
Well, the roots have a lower water potential than the distilled water. The distilled water has a higher water potential. This means that the water will move from outside of the roots into them through osmosis.
As the water enters the roots, it will be compared to the stems, which have an even lower water potential of -6 bars. The water will then move into the stems because the stems have a lower water potential.
This continues.
As the water enters the stems, it will be compared to the leaves, which have an even smaller water potential of -15 bars. The water will enter the leaves.
Then it will be compared to the atmosphere, which has -1,000 bars. So the water will continue to move up until it's in the atmosphere.
In this example we have provided, water is moving up the tree along the water potential gradient.
Now that this is understood, we want to introduce some new terminology. The terms hypotonic, isotonic, and hypertonic.
We are going to use a cell that has 3 little letters inside. The letters are being used to represent solutes. We will also be putting the cell into 3 different environments to show what will happen using our new terminology. The cell has a water potential of -2 bars.
For our first example, the cell is in distilled water. Because the cell has more solutes than the water surrounding it, the cell is hypertonic to the solution. When left for a little while, the water will enter the cell, leaving the area of higher water potential and entering the area of lower water potential. Please take note of how we use the word hypertonic. A cell is hypertonic to its surrounding if it has more solutes than its surrounding.
Let's say we take the same cell and we place it into a solution with an extremely large amount of solute. The water will move out of the cell into the surrounding environment, leaving the area of high water potential and entering the area of low water potential, which follows what we said before.
Now, what is isotonic? Isotonic is an equilibrium met between 2 substances. For example, if the same cell were placed inside of a solution with a water potential of -2 bars, there will be no movement of water because both areas have the same water potential. If both have -2 water potential, there is no lower water potential for the water to flow to.
Does that make sense? Say yes. Time for review! So, water potential is solute potential plus pressure potential.
And the way to find solute potential is found with the equation -I CRT.
Pressure potential has to do with plants and turgor pressure.
Trees are a really good way to understand how water potential works as a gradient, pushing water through the roots to the leaves.
And remember your terminology of hypotonic when solution is smaller than the surrounding environment, hypertonic when the solute is larger than the surrounding environment, and isotonic when you have reached equilibrium. Review time, my children! It's time for a review. It's supposed to be the penguin. High water. See? So, higher the solute, the higher the... I hope you've learned. Thanks. Bye!